Hello and welcome to physics. We're going to look at circuits in our IGCSE textbook. That is unit 8.04 to 8.07. Okay. So the first thing that we are going to look at is the basics of circuits. Okay. Now there's a very good analogy that we usually use to understand how circuits work. There's going to be three things that we're going to look at. We're going to look at the current, which is the flow. Okay, the potential resistance, which is, or the potential difference, which is the amount of energy. In this case, it's the height of the water tower, and the resistance is the thickness of the pipe. So if we look at it, voltage, or the potential difference, is the potential to flow. It increases as the further distance up. Okay, so the higher this thing is up, the more force it has pushing the water down. We're going to look at that analogy. Then resistance is the width of the pipe, how quickly the water can flow through, and the current is the actual water, and it increases when the voltage is high, a greater potential, and the resistance is low, a wider pipe. Okay, so we're going to look at each one of these three now individually: current, then voltage, then resistance. Okay, so guys, the idea is that there is a relationship between these three happening. We have the voltage, which creates a force or a push, pushing the current, which is this guy here, the amperes, through the circuit. He says, currently I'm not traveling very fast, so the guy going through is the current, and the guy resisting him is the resistance. So there are three people here: the voltage, the current, and the resistance, and the three of them have a unique relationship. So first, let's look at current in a simple circuit. Okay, so electricity is when electrons move around the circuit and carry energy with them. Okay, so electrons are moving through the circuit, carrying energy with them. Okay, if we look at the next analogy, we can see that there is electrons traveling through the circuit. They receive energy at the cell, and then they deliver the energy at the resistor. In this case, the resistor is a lamp. Okay, back to our previous slide. Okay, so as we said, electricity is when electrons move around the circuit and carry energy with them. Current is defined as the rate of flow of electrons. Okay, so what is current? Current is how quickly these blue electrons flow through the circuit. If they flow quick, it's got a big current. If they flow slow, it's got a low current. Okay, so each electron has a negative charge. Charge is measured in terms of Coulomb. We can work out how much charge flows in a circuit using the equation. The charge in Coulomb is the current times the time. So what are we calculating? When we're calculating the amount of electrons is equal to the flow of electrons times the time. Okay, so two concepts here: the current. We can actually not define current if we don't define charge first. So charge is electrons, and current is the flow of electrons, what we call the flow of charge. Okay, and you need to learn this definition and this equation. You've memorized this triangle in the beginning of IGCSE. Okay, so if we want the current, we close the I and we've got Q over T. If we want the charge, it is I times T. Okay, so back to our next slide. Here we will see the three things. Okay, so the voltage comes from the cell, the pushing the electrons through. The resistance comes from the resistor, in this case the lamps. The current doesn't come from anywhere specifically. There is no part of my circuit that gives current. Current is a response to the potential difference and to the resistance, and we'll look at. Okay, so now we'll be looking at a few questions here. We've got our triangle here in the top right, left-hand corner, so we can go ahead. So firstly, if I want to calculate the current and the time, I want the charge is I times T, 5 times 2, and that gives me 10. Okay, if I want the charge, if I want the time, it is Q over I, so 0.4 divided by 1 gives me 0.4 seconds. If I want the time again, 20 divided by 0.5 gives me 40 seconds. Okay, if I want the current, then it's Q over T, so 50 divided by 250, and that gives me 0.2 amperes. And then if I want the charge again, I times T, 3 times 60 gives me 180 coulombs. Okay, so that is in table form. Let's read a few questions. A circuit is switched on for 30 seconds, a charge of 3 amperes. How much charge flows? So we want Q, I times T, 30 times 3 gives me 90 coulombs. Okay. During electrolysis, a 6 ampere was passed through some copper chloride and a charge of 1,200 coulombs. How long was the experiment on for? Now, if you don't know what electrolysis is, this is a chemistry experiment. Okay, so we want the time, so it's the charge, 1,200 divided by 6, so that gives me 200 seconds. A bait lamp is switched on for 10 minutes. Danger! Why? I can't use minutes in this formula, so I must convert it to seconds. 10 times 60 gives me 600 seconds. It works for a current of 0.5 amperes. How much charges flows? So 0.5 times 600 gives me 300 coulombs. Okay, so the next one that we'll be looking at is, we've looked at current. We're going to now look at the voltage, which is the potential to flow, okay, or the push. So what is potential difference? The voltage between 2 points is the work done per coulomb traveling between 2 points. Okay, so think of the guy pushing the other guy. The work that that guy is doing, pushing it, okay, per coulomb of charge, per electron, pushing it from one point to another. So the voltage is the work that we measure in joules divided by the charge. So the unit is supposed to be joules per coulomb, but this guy with the surname of Volta, the guy who discovered it, renamed this unit after himself so that we don't have a complex unit, but just we call it 1 volt. Now please note, you'll see often that they speak about voltage. The correct word for it, as we've seen, is potential difference. Okay, so potential difference has been, now the unit for potential difference is volts, okay, but this term voltage has been used so often that it is also acceptable now. So you would call the potential difference the voltage. We will never call the current the amps. That would be wrong. Okay, and we would never call the resistance the ohms. Okay, so the voltage is the only one that we can call according to its unit. Okay, and the symbol V and the unit V is actually the same. For all the others, it's not. Okay, so what is volts in base units? It's joules per coulomb. Okay, so if we move on, here we see our circuit. We said we supply our potential difference. The force pushing these electrons comes from the cells. Now, what's going to happen when I put more cells? A bigger force. Firstly, if we look here, we see immediately that the electrons travel faster. Why? There is a bigger push, a bigger force. Secondly, we see that there's more light. Obviously, if we compare the two, this one has more light because the cells gives more energy. Okay, and a rule with electricity is that all the energy given by the cell must be used by the resistor. So here there's one cell, one light bulb using that. So if we double the cells, there's double amount of energy that has to be used by the resistor, in this case a lamp. So as we look at a few questions here, we have our triangle here in the corner. Okay, a battery does 9 joules of work, so we've got the work. It transfers 6 coulombs of charge. What is the battery's voltage? So we have the W, we have the Q. So 9 divided by 6 gives me 1.5. Okay, A power pack does 100 joules of work transferring 20 coulombs of charge. What is the voltage? So 100 joules divided by 20 coulombs gives me 5 volts. A 9-volt battery transfers 20 coulombs of charge. How much work does it do? So we want the work, the voltage times the charge. 9 times 20 gives me 180 joules. Now the next current refers to the same battery. Okay. If the current in the battery is 0.2 amperes, we just saw that Q is I times T. So 0.2 times how long was it used for? Okay, so charge divided by time. Sorry, Q divided by I gives us T. We want the time. So 20 divided by 0.2 gives us 100. Okay, so 240 joules of work is done to a 12-volt motor. We've got the work, we've got the voltage. What's the charge? 240 divided by 12 volts gives me 20 coulombs. Okay, now once again, this question refers to that one. If this motor was used for 40 seconds, now we have the 20 coulombs, we have the time. Q divided by T would be the current. Okay, so what would be the current? 20 divided by 40 is 0.5 amperes. Next, we'll look at the resistance. Okay, the pushing back against the flow decreases if the pipe's width is bigger. So we're going to now look at what in the circuit is the width of the pipe. Okay, so resistance. Now, firstly, the guy who discovered resistance is George Simon Ohm, and the unit is also named after him. We use the symbol omega, okay, so ohm and omega. Okay, so resistance is anything that resists the current. And once again, that picture in the beginning where the guy was pulling on a rope, making it more difficult for the current to flow. Anything that resists the current. It is measured in ohms, a unit named after me, this guy called Ohm. Okay, he discovered it. Okay, so the resistance of a component can be calculated using this equation. Ohm's law, welcome to this. Resistance is voltage divided by current. Or here's a triangle. V, resistance, R is V over I, or V is I times R. And this is the formula that you'll use by far the most often. Okay, so one of Ohm's laws was, okay, Ohm's law is a special case where the voltage is proportional to the current. For example, consider a resistor. So if we have a specific type of resistor, okay, and we use current over voltage here, we see that the irrespective of how big the voltage gets, the current increases in the same rate. We have a direct proportionality. So when I over V is directly proportional to each other, that means that the resistance stays constant. Now this is rarely ever happens. Most resistors that we know will never give us a straight line. It will give us a curve because the resistance changes the moment the temperature changes. Now think of any device, a light bulb, a washing machine, a microwave, whatever uses electricity heats up. And the moment it heats up, the resistance changes. So this is a theoretical resistor. This is why we're trying to get our light bulbs and all these things to work with as least resistance or least loss of heat, so that the resistance can stay constant. So when we have a theoretical resistor that never changes its temperature, we call it an ohmic resistor because it obeys Ohm's law, the one that we looked at here, perfectly. Okay, the moment a resistor does not keep its temperature constant, meaning the resistance changes, it doesn't obey this formula all the time. Okay, so here we see that the resistance is constant irrespective of how much voltage flows through it. Questions based on this formula. Okay, so firstly, resistance is anything that opposes electric current. Okay, so we can see that the resistance and the current are inversely proportional to each other. So the moment there is a high resistance, there would be a low current, and the moment there's a low resistance, there will be a high current. So let's use the formula a bit. A bulb of voltage 3 volts, we've got the voltage and a current of 1 ampere. What is the resistance? 3 divided by 1 gives me 3 ohms. Okay, a resistor with a voltage of 12 volts and a current of 3 amperes. 12 volts and current, we want the resistance. 12 divided by 3 gives us 4. A diode with a voltage of 240 volts and a current of 40 amperes. So it's 240 divided by 40, which gives me 6 ohms. And then a thermistor with a current of 0.5 amperes and a voltage of 10 volts. So we say 10 divided by 5, and that gives us 20 ohms. Now, if you don't know what a diode or a thermistor is, we'll discuss that in a further video. Okay, so let's quickly look at resistance. We said resistance is anything that opposes the flow of charge and it uses energy. So the light bulb here is a type of resistor. A light bulb uses energy. Okay, so the energy given by the cell is transported by the electrons and delivered here by the resistor, and then the resistor uses it. Okay, so what's going to happen to the flow of the current the moment I include a second resistor, if I increase the resistance? Okay, and what you'll notice is that the current moves drastically slower. Obviously, there are two resistors, so there are less energy. The energy of this one must be delivered to both of these light bulbs, and because they are equal in brightness or equal in strength in this case, the energy is shared equally amongst them. Okay, so we see here, compare it to the previous one, when we have low resistance, we've got a big current, and we've got big resistance, two resistors next to each other, we've got a small current. Okay, so less resistance allows more current. So what are the four factors or the four component change? What four components change the resistance of a wire? So if we think a wire or any type of resistor, there are four things that influences how much resistance it has. Firstly, the thickness. Now if we look here, this one only has a width that allows one electron at a time. This one is wide enough to allow more electrons at a time. So the thicker the wire, the less resistance. The thinner the wire, the more resistance and the less current. So less resistance, more current, more resistance, less current. Okay, the next thing is the length. Okay, a short resistor will allow more resistors of electrons from the start to the end. Okay, a longer one, it will take much longer, so therefore it will have higher resistance. This one will be much shorter, so therefore it goes quicker. Okay, and then the material. So if we look here, we've got a bad conductor, and here we've got a good conductor. Okay, and we will look at what is good conductors and bad conductors. Something like copper is a very good and very cheap conductor, therefore it allows a lot of electrons to flow. And then lastly, the temperature. So when the material gets hot, the resistance gets more. Okay, if it's a non-ohmic resistor, so the more temperature, the less the current and the more the resistance. I hope you have understood this lesson. If you've got any questions, please feel free to ask. Thank you very much.